Okay, welcome everybody to the Direcectives-based GPU Programming course. My name is Vasilios Karakasis, and me and as well as Markus Wettstein from PGI will be the instructors for this two-day course. I am computer scientist by training. I work here at CSCS. My main task currently is I'm in the technical committee of OpenACC representing CSCS, and currently I'm working on a different project that's about regression testing and continuous integration of HPC applications. I'm the lead developer of a software we're developing here. And my PhD was on node-level parallelism and CPU architectures and this low-level stuff. So just before starting with the slides, I wanted you to know that this is the GitHub repository of the project. I'm going to go through it later on through the day. I'm just give you a heads up, because if you go there, then inside the slides, there are already the slides of the first day so that you can follow them as we are talking. And so, and here is the schedule of the course. We're gonna, it's not exactly strict, but this is the how it's gonna be. So the first 15 minutes, I'd like to I presented myself. Markus will present himself as well, and then we will go quickly through you just to tell us your expectations about the course, your experience with perhaps programming, and what we are actually doing in your research, and why OpenACC or this course is useful to you, so that we can adapt it during the way. Then I'm going to give you an overview of GPU architecture in the HPC, how we gradually shifted from the MPI paradigm to GPU architectures. And I'm going to give you also an overview of what this machine is, how it looks like architecturally, and what are its quirks and all the little details. Then, before lunch, I'm going to give you a short introduction to the pit-stained environment, where I'm going to give you the passwords and the accounts for the hands-on session, and you're going to try to log in to see that everything works. Then we have a lunch, and then we move into OpenACC. We're going to cover all the basic directives about the execution and the memory model. Then after the coffee break, we're going to present you briefly a couple of tools for debugging and profiling. And then we start the hands-on sessions. We have several exercises that start from very basic stuff and go to more advanced topics. And the idea is that we will go through them. We will leave you also with some time to exercise yourself on the theory we have just presented, so that you get more used to the thing. And then we present the solution. We play around interactively with exercises. Second day, we get into the advanced topics. So Markus is going to present the so-called activity queues and streams. Then I'm going to present how OpenACC can interoperate with CUDA and MPI, which is important, and RDMA concepts and these kind of things. And then again, Markus is going to present the concept of deep copy. We're going to see all of this, what's going to be, and then again we'll have hands-on sessions on these topics. So I'm going to now pass the microphone around. First, Markus, can you present yourself a bit? It's open, right? Okay, that's fine.
Hi, my name is Markus Wettstein. I'm a DevTech engineer in the PGI Compilers and Tools group within NVIDIA. And I work a lot with application programmers using OpenACC and various other GPU programming paradigms. And I'll help Vasily with the course as he outlined already.
Hi, my name is Ravi Patel. I'm a postdoc at Paul Scherrer Institute. I work with advanced Fortran and Python for lattice-Boltzmann method-based code development. And I have my own open source code, which has reactive transport capabilities, and we work also on multi-scale modeling in that context. Yeah.
Yeah, hello everybody. I'm Marco Bacci from University of Zurich, and I work on molecular dynamics. I have been developing methods for sampling, and now I'm coupling our software with GROMAS, which runs also on GPU-enabled nodes, and so that's why I'm here.
Hello, my name is Barbara. I come from the University of Zurich, and I work on computational fluid dynamics, so I need to program to implement the mathematical model, and since I've just started a new project, I would like to use GPU indeed.
Hello, my name is Jan. I'm a PhD student at Erlangen-Nuremberg University. I mainly program or do code generation, mainly in phase field simulations and LBM models.
Hi, my name is Jarunan. I am working at the Scientific IT Services of the ETH Zurich, and my background is in MPI parallelization. I was a software developer, and I'm interested in optimization on GPU as well, as now we have GPU cluster from the ETH too.
Hey, I'm Michael. I'm from University of Amsterdam, but like in last year, I've been working as a machine learning researcher in a company that you've never heard of, and that's why I need to know about GPUs.
Yeah, I'm Marco Schweitzer, and I'm working for the same company. It's a trading company, and we want to use like GPU for optimization.
Good morning, everyone. My name is Marco Alemanno. I belong to Italian Air Force Meteorological Service. I'm quite interested in GPU programming because in my center, we have been trying to develop a GPU version of our weather forecast model. But my experience in GPU programming is quite poor, so this course is very important for me and for my organization in order to better develop the model, the forecast model.
Hi everyone, I'm Onur Çatmabacak. I'm a PhD student at University of Zurich. I'm working in the Institute for Computational Science. Currently, I just use Python to post-process a huge data of high-resolution cosmological zoom-in simulations, but they're right now just parallelized with CPU. And in the future, I'm really interested in developing the GPU version of the code, which is called Gizmo.
Hi, I'm Radim. I'm a PhD student at UC Lugano. I'm working on a sparse direct solver.
Hi, I'm Luca. I am an economist, so I guess I'm the weird guy here. I work at the University of Zurich as a PhD student in the Department of Finance. And my interest is mostly in macroeconomic modeling. And our research group has been trying to develop new solution methods for macroeconomic models, which involves a lot of effort in trying to learn computational techniques and then tools, of course. So,
great.
Hi everyone, my name is Mathieu Leclerc. I'm working at ETH Zurich as officially say a model developer. My background is more in applied math, numerical analysis, things like this, and I've done my PhD in ocean modeling. And right now I'm working in the land climate dynamics group, and we have a project that is where I could take advantage of this. Is we are working in coupling Cosmo, which is the weather forecast model of the Swiss Meteorology Service, And we're coupling it with another land model that comes from the US. And as you know, Cosmo has already been ported to GPU. And we've been successful recently to couple it with our model that is running on CPU. And so we take advantage of both on the end, but there's still a lot of room for optimization.
Yeah, good luck with Cosmo. I have worked a bit with it, and it's a beast.
So my name is Lia Sartori. I'm a PhD student at ETH Zurich. So I am an observational astrophysicist. This means that in general I'm working with data from telescopes, and this does not involve a lot of programming. But now I would like to, forward modeling the activity of supermassive black hole with time. And since this can be quite computationally expensive, we want to simulate the whole universe on, let's say, weak resolution. I would like to take advantage of GPU programming for this.
Great.
Oh, hi, I'm Pirmin. I'm a PhD student at ETH Zurich, and I'm working on Higgs analysis in a CMS experiment, and we're also working on a lot of data and also machine learning applications. So I hope also this helps me.
Hello, my name is Rafael. I work here at CSCS. My background is a bit of machine learning and material science, and I work mostly here with the regression software together with Vasily. And I'm interested in the course because just looking forward to participate in projects related to GPU programming and those things.
That's right. Okay, just a final question from my side. So, who of you are using C++ mostly for day-to-day, or for their project that they C or C++? Okay, and the rest of you are Fortran? Okay. Okay, luckily we have the hands-on sessions are both languages, but some of them are one of them is just Fortran, and the other one is a couple of them are only C++. So I hope that I won't disappoint you. So let's move on. So this is the overview of this session presentation. So I'm gonna give you a background why the architectures have moved to GPUs. What are their differences with CPUs, and what are the challenges for the HPC applications that they want to basically scale to these new kind of architectures. And then I'm going to present you briefly how a GPU looks like and how the execution model is and its memory model, which are somehow different from what we know already from the CPUs. So, as you have noticed, the last years, at least 7-8 years, there is a trend towards more parallelism on the computing node. So you see that we have lots of multi-cores, lots of cores. Every year, basically, the cores of every new generation gain more and more. So you can see that now the Broadwell processors, I would say 10 cores. Each core has also 2 hyperthreads, so that makes us 36. The same for the Power 8 from IBM. There you see 12 cores by 8. So it's quite a lot of parallelism. And then you also have, to the extreme of this parallelism, you see the GPUs, where you have thousands of cores. We will see how this parallelism can be achieved. And then you see also this great trend. In the past, it wasn't like that. But this is, for example, just to show you visually what these parallelisms look like. So on the left hand, we have, this is a pitch-stained node. On the left hand, we have a Haswell processor, where you see it has 12 cores. Each core has also 2 threads. And on the right hand, and the large L3 cache, and every core has its own L2. And on the right hand, you see a GPU. And the green small dots are actually the processing units. So you see that there is lots of parallelism that needs to be exploited. And if you don't do that, then basically you cannot efficiently use today's computers and supercomputers. So, but this wasn't the case for a lot of years. So from whenever we started with parallel programming, the standard for HPC applications was the MPI. So basically what we were doing, we were just using MPI. Usually the architecture was we had clusters and every node has just a single or two nodes maximum, two CPUs on a single node maximum. And then we didn't have all this notion of parallelism. We just had OpenMPI over large clusters, and the idea of programming that was fairly simple in a sense. You decompose your problem in chunks, and you communicate your chunk to different processors, and that's it. And then you have parallelized your program. But this is not enough anymore. Okay, you still have to do this because you still have to spread it over your compute nodes, which is still MPI, but then what happens on the node? So the other thing was that this was kind of a freelance because every generation, as you remember, up to 2005, the clock frequency was exponentially increasing. So every almost 1.5 years was doubling. So that means that I don't care about my single node performance because I know that the next generation my code will be much faster. I just have to wait. Now this is no more the case. So this is what I was explaining right now. So this is how the transistor density has evolved over the years. And you see that it scales up to today. The transistor density still scales in an exponential fashion. So every 18 months, we have twice as much the transistors inside the processor. That's because the technology advances, and then basically the technology makes the transistor much smaller, so we can accommodate much more circuits inside our designs. And does anybody know what this nanometer scale that we are talking about densities? This nanometer scale is basically how way two gates can be in an integrated circuit. So the larger it is, the less things you can fit, the less circuits, the less components you can fit in a certain area. So every time the technology advances, this density increases, and so we can fit more things, so more circuits, and make our processors give more components and then make them faster. But there is an interesting trend though. So this is the same plot, but using frequency on the y-axis, and here is the same. And you see that 2004, we have a plateau here. Up to this point, again, we had every 18 months, the frequency was doubling. And suddenly at 2005, there's no more frequency increase. And so this is the time where the freelance of single node performance was over. We need to find out different ways to exploit parallelism on the node, because just waiting and magically having our application run faster with the next generation wasn't anymore the case. And indeed, here is the single thread performance, where you see that again around 2005 and a bit later on, the performance of a single thread, although it scales, it doesn't scale in the way it used to scale in the past. So parallelism is quite crucial. But why we stopped doing that? Why architects stopped increasing the frequency? And it wasn't just to make our lives harder. It was due to technical limitations. The first and foremost limitation was power consumption, because power of a processor scales with the square of the voltage, and in order to get higher frequencies, you need higher voltages. And the reason for that is that you need to be able to differentiate the states of the on and off, the one and zeros. So basically you have to increase the frequency, to increase the voltage to sustain higher frequency. Those that you have played with overclocking, you maybe have seen that you have to increase the frequency to get the voltage to get even higher frequency in your processor. But the problem with that is that, okay, we're not just increasing the frequency, but we're also making the transistors shorter. So smaller and more dense. So this increases the power density. And it was around 2015 that I think back then the Itanium, or one of the top processors, the power density was 130 watts per square centimeter, if I'm not mistaken of the number, which is almost very close to what a nuclear reactor power density was. So this couldn't scale. And the second thing why frequency scaling was not beneficial, not to sustain the high throughput, because, okay, I have like 4 gigahertz, but I need to be able to finish the instructions at this rate, because otherwise, effectively, I'm not running at 4 gigahertz. Then the architects had to design very, very deep pipelines. Deep pipelines mean a pipeline is when a process executes an instruction, then this instruction goes through certain stages, and it doesn't execute all in one. So every instruction starts on the first stage, then the second instruction starts one stage after, and so on. So then you can have very high throughput in instruction. In order to sustain high frequencies, architects had to design very, very deep pipeline to split the execution of instruction in very, very, very small stages. But the disadvantage of this was whenever the process has to wait for something, because I didn't find my data on the cache, then I had to flash the pipeline and wait and spend so many stages waiting, which is basically cycles. The same was when I'm taking a branch and I has mispredicted. Then I had to flash the pipeline like 10, 15 stages, which means I was losing 15 cycles and more. So this couldn't scale. So for these reasons, architects moved to multi-core. So the technology exists that we can still shrink transistors, but we cannot scale the frequency. So what else we can do? We can gain performance by putting more parallelism on the chip. And this is how the multi-cores started, and then we had in 2005, if you remember, we have the hyper-threading technology, then we have the Intel Core architecture, which was like the 2 cores, and so on. So how we can increase the performance of the application run on processors? First is, as I said, increase the clock speed, but that's not the case anymore. So the second is, increase the number of operations per cycle. So here there are 3 levels of parallelism that are quite important in modern architecture, and you will see them also in the GPUs. So first of all is what we call vectorization. So vectorization means that with the same instruction, you apply the same operation on multiple data. That means I'm doing an addition and execute a single instruction, but I'm doing the same operation in like 8 doubles. Or if you take it to the extreme, we do it in 32 doubles on GPUs, the same instruction. So with one instruction, we basically do effectively 8 or 32 real instructions. The next thing is instruction level parallelism. This used to be also in the old times, even before the multi-cores. And this is that a processor usually is not just executing one instruction at a time, but instead it executes lots of up to 4 instructions, for example, the modern processor in the time. So they fetch 4 instructions at the same time, and they schedule them to execute them so far that they don't have dependencies with each other. And this is called instruction level parallelism. This is quite important also on modern architectures. And finally, it's thread level parallelism, which is what multi-cores are, and which all the modern architecture are going towards this direction. And this is that on the same there you have you have either the so-called hyperthreads or you have the multiple cores. And this number is always increasing. The third is that your code should not make the pipeline stall. That basically it's two basic things. One is you should use as much data as possible and as often as possible, so as to make your algorithm exploit this, what we call temporal and spatial locality. The second thing is that your algorithms must be regular enough, so you don't have to branch a lot around. And these are two major points of performance degradation. And so both us writing applications, but both from the hardware point of view, both try to optimize those parts. So we have the hardware that have fancy techniques for branch prediction, large caches, and we have several components for on-chip parallelism, but then the application has to be able to take advantage of them. So again, the same statement, look just again about the frequencies. So for example, you see that the 4-core castle processor 3.5 gigahertz has the same power consumption as a 12-core at 2.6. So you see that increasing the cores is the way to go. And going to the extreme, Pascal GPU with 3,582 CUDA cores runs only at 1.1 gigahertz. So it is extremely power efficient. But again, we need to be able to program those machines. If you have any questions, just interrupt me during how I'm going on. So, as I said, again, this is the trend where every generation will have more cores and more types of core and so on and so forth. We have either more generic cores or more specific that they're good at doing computational stuff like the KNL or the GPUs. And then now we have, for example, with the new generation GPUs, the Volta, the latest generation, we have also more specific processor just to do deep learning, to be able to do these matrix multiplications that are needed in this type of computation. But you see that parallelism is growing. So now let's see how, at the high level, what are the key differences between the CPU and the GPU. So this is like an abstraction of the die area of a CPU chip. So you see that the most and almost half of the die area is obtained, or even more, from caches. So that's why, I mean, both GPU and CPU architects, they have the same technology in their hands, but it's different how they arrange the things on the chip. So CPU favors, okay, I have less processing units, I have very large cache and very large control unit. And there is because those machines are typically designed for latency-bound applications. So applications that they have to hide, you have to hide the latency of getting to the memory by actually having a very large cache, and they're also designed in the sense that they can afford some random accesses, because the workload of the CPUs is not just our science. It's very, very wide, from the operating system to database applications, web applications. All this stuff must be able to run on the CPU, and that's not the case. So that's why it is much more general purpose. That's why they have this all fancy logic about out-of-order execution, where multiple instructions are fed from the memory and they're executing out of order. They're not following the order of the program, so as to increase as much as possible the throughput. But the downside for this is that you have to spend so much die area on control and on large caches. Now, the GPU is completely at a completely different end. So almost the majority of the die area of the GPU is occupied by actual processing cores. And these processing cores are very, very simple ones. They have nothing to do, just compare a single CUDA core with a CPU core is very, very simple or naive. Just executes instructions in order, in a specific way. No fancy logic, no fancy branch prediction software and all these things. It's just focused on computation. And for that reason, they don't have very large caches or control logic. So let's go a bit to the next slide. So let's see how the GPUs are scheduling multiple threads. Okay, so you see that on the CPU you have a limited amount of threads that they can run. Okay, assume that you have because just two. I mean, in a 4-core CPU, you may say, okay, I can run 16 threads, but how this can happen? So there is not enough space. So this happens that threads 1 run, then it's processing, then it's waiting for memory. But you see here the wait time for memory is generally less compared to the GPU because you have very large caches. So it's very likely that you will find what you need in the caches because they're quite large. They have advanced architecture inside them so that accommodate more data. But the downside is that you cannot have a lot of threads on the same processor. And if you want support to oversubscribe a core, then you have to involve the operating system as well to do the context switch of you. The context switch is a very high. It's an operation that basically takes some time. So what it does, it saves all the registers of the current thread and then moves to another thread. So you cannot have like thousands of threads on a 16-core, for example, CPU and expect your application to scale beyond 16. So this cannot happen because the resources are there. Now on the GPU, it's a bit different. So the GPU have lots of threads, or thread bundles that we will see later on. And those threads execute, and when they go and wait they do a memory operation and wait, then they have to wait. You don't have large caches to just quickly get it. Okay, you have caches, but it's not as efficient as on the CPU. So how do you hide this thing that you cannot hide with a cache? You hide with more parallelism. So I'm running this, then while I'm waiting, I'm going to schedule the rest of the threads to run. So these are the two major ways to cover memory latency, and that's the two different, so to say, schools. One is you have very large caches and you expect to fit everything there. The other is have very small caches, but I have lots of parallelism, and I expect to hide the latency if I have enough work to do. If you don't have enough work to do, then there is a problem. And the other thing for the GPUs, if you notice, there's no this little black thing. So when you switch from thread bundle to thread bundle, you don't have any context switch. We'll see how this can be achieved. And that's extremely efficient because it's the only way that you can, basically on the GPU, you can have, like we said, 3,500 cores, but you can run, you can have, you have like 3,500 cores there, and you can have 3,500 threads. So it's an extreme number. If you try to have so many threads on the CPU, you will end up spending all your time in the kernel doing the context switches. On the GPU, it's extremely efficient, and we'll see how this is achieved. So, so the thing is that applications are not designed for, you might have seen it also. I mean, most of you are working on projects. You said that I want to parallelize my application to get advantage of this very high parallelism. And as you might have seen, and you might also have experience already with that, is that there's not, in order to exploit so large parallelism, we need to be able to extract this fine-grained parallelism. To be able, for example, to take a loop and execute each iteration of the loop in parallel, ideally. But this is not very easy to achieve because we need new programming model paradigms, new algorithms, and current code must be refactored or rethinked of so that it can take advantage. So this is a very hard task. And as a result, currently the compute nodes are usually underutilized because you're not getting the full power of what the GPU is giving you or even what the multicore is giving you. And there's nothing else we can do about it because that's the trend. We saw it before. Parallelism will increase. So we have to do something about that. Any questions so far? Okay. So I will move on to to more details now about the GPU architecture. So this is one Pascal GPU is as the ones that we have on Pitstain, and we're going to work on those during the course. Again, you see this is a more accurate diagram where you see again how many cores you have. So this is how it is organized more or less. So you have you notice those little boxes here. These are called the multiprocessors. These are the key components of the GPU, and each of those multiprocessor has 64 cores, and it's comprised of so many smaller cores. So then you see that where is the global memory here? I can't see it. So then you see. Okay, I would go to the first one because this is not a very good slide. To the next one. So this is more important. This is how this multiprocessor, that in the terminology of the GPU is called simultaneous multiprocessor. So this is a multi-core basically component that has 64 single-threaded cores that they're very lightweight. Then another thing is that these cores are not independent between them. So these cores execute in all of them execute the same instruction. All of 32 of them, every 32 of them, they execute the same instruction. So there's no way that one core can go a bit farther away, the other a bit behind, and so on. All of them, they execute the same instruction in batches. And these are called warps in the terminology. These groups or bundles of 32 threads are called warps. Okay, in the Volta, in the next generation architecture, there is a bit more flexibility on that, but we're not going to cover it because I think that's much more important to get this notion of warps and this way of execution. Now, each of these SMs had a very, very large register file. Does anybody know how large is a register file on a CPU? How many registers do you have on a CPU? It's even if you include all the different vector register and stuff, you don't have, I don't think, more than 64 registers with control or a bit more. Here you have 256 kilobytes of register. So if you divide by 32 is like 30K anyway, you have thousands of registers. That's a completely different notion. And we're going to see why you need so many registers. Any idea why so many registers are needed? We will see in a while. And another component of this SM is the warp scheduler. This is an important component because if you remember the slide I've shown before, the GPU tries to hide latency, memory latency, through parallelism. So you need to have an efficient way to, you need first of all to have lots of active threads waiting to run. So every time the warp scheduler gets a thread to run, and not a thread, a warp to run, it runs it. But if one of the threads of the warp does a memory access and then it's not a hit or it should wait the memory, then the warp scheduler should find another warp that is ready to run and schedule this for running. And there should be enough warps there so that it can hide the latency of the first warp that was waiting for memory access. And the next thing is that this scheduling is very, very fast. And we will see how the register, this huge register file, helps with this thing. And finally, another important component is the shared memory. There is all the threads, all the cores here, they share. It's like a level 1 cache that can be used, that can be either hardware managed or software managed. Software managed means that you can see it from your program, and you can say that I want to put this array on this structure, on this shared memory. Any question here? Okay. Now, another difference is that on CPU, the execution model is it's like very old, from the 40s, is the von Neumann model. So you have your program in the memory, you read its instructions, and you have your data again in the memory. The memory is a shared address space. All the multi-cores, all the cores in a multi-core, they share the same address space. No need to fuss about. All your data is there. Only if it's shared, then you have to care about race conditions, but that's another chapter. On the GPU, however, this is not the case. GPU and CPU, they have different memory spaces, not only physically, but also virtually. So since they are different virtually, then you have to manage the data yourself. So the transfers, everything. So you have an algorithm, and then you want to execute that on the GPU. First, you have to copy the data that the algorithms will use to the GPU, then compute there, and then move the data back. So this all is manual. So you have to do it yourself. So the CPU this model is called host-directed execution or host accelerator model, where the host runs the operating system and basically directs the execution on the coprocessor or the accelerator or the GPU. So the allocations, the transfers, and so on. There is, however, recently in the recent architectures of GPUs, what it's called the unified memory between CPU and GPU that makes life easier. Again, physically, the address spaces are different, but virtually, they seem to be the same. So when you access something from the GPU, then the kernel CUDA driver, the CUDA kernel driver will do the page migration for you. We will see that in a while. This is an alternative model which gains access, gains interest, It makes life easier, but still, it's very important to know that behind the scenes, that these data transfers have to happen. Okay. Now, let's see some terminology. I said before that you want to run an algorithm, GPU. So what you do is basically, first of all, you need to, okay, before I omit the data transfer part for the moment. So the code that runs on the GPU is called the kernel in the terminology of the GPU. So it's basically the function that will run your code on the GPU. So the host launches kernels on the GPU. This basically, technically, it transfers some parameters to the GPU, and then basically initiates the execution. Now, how all this huge parallelism that we've seen before of the thousands of threads is organized? Obviously, it must be organized somehow. So every kernel comprises groups of threads. So each group of threads is called the block in the CUDA terminology, or gang in the OpenACC terminology. So every kernel has several such groups of threads. Now, each of this block of threads may only run on one of the simultaneous multiprocessors that I've shown you before. These key components that they have the shared memory on them, and yes, they have the shared, and the GPU has multiple of them. The threads of a block may not run on different simultaneous multiprocessors. They will just run on this same multiprocessor. And multiple blocks may be accommodated in a single SM. Now, how this is determined for several reasons. Are there enough registers to accommodate them, or are they enough shared memory, and so on? Now, all of the blocks basically that have actually landed on the SM and they are executing on them are called active blocks, and all of their warps, that is, their 32 thread bundles, are called active warps. But let's see how a bit visually how this works. So assume that we have a GPU with two SMs, those multiprocessors. So every multiprocessor necessarily have a large register file, shared memory here, and here is the warp scheduler. And here is your application that has produced, your kernel has produced so many thread blocks. Now, each thread block has a set of requirements. So first requirement is how many registers it needs to run. And that's, for example, that's how this is determined. For example, you have your code, as in the CPU, basically, and how many registers does one thread needs? Say 10. Then if my block has 128, I will need 1280 registers to accommodate all the threads of my block. Then my block needs also 1 kilobyte of shared memory, because there I have allocated a temporary array. And these are the requirements of the kernel. So then what happens? Then the runtime determines that, okay, with those requirements, here I assume that they don't have any requirement of shared memory, I can just accommodate four blocks on one SM. So here I took 8 blocks and put them for running. Now, all this, an important thing here is that all of these blocks, they share the register file. They basically partition the register file, and each one has its own portion of the register file. So when they are moved there, each one has its own registers. On the CPU, it's not like that. Yes, please. Just let me give you the microphone.
For the terminology, the register file, is it mean the task that they have to do? Like the task that we're assigning?
I'm gonna explain that. So, assuming you have to do your algorithm basically does like copying an array. So you say xi equals yi. So how this translates in processor instructions. So this will translate first load from a memory location which corresponds to the xi, load something to a register, and then store that register to another file location. So the register is where you actually have your current state of execution. So even on the CPUs, it's basically all the memory, all the operations you do. The idea is you get data from the memory into registers, then you do your additions, multiplications, all your calculations there, and then you store your data back from the registers to the memory. So it's like the register file, you can imagine like the scratch pad of the processor, where it does all its operations. So the same is here. So the register file is partitioned, and then we have the warp scheduler picks warps to schedule for execution. Okay, so here it picks this warp, which is ready, then picks another one, and so on. Every time a single warp is running. And the same independently from the other SM. Now, what is the key difference here with the register file, with this register file and the CPU register file, besides the size? In the CPU, you cannot partition the register file. So when you need, each core has its own register file, but assuming you have more threads to run than available cores, then you cannot partition your register file among multiple threads, as on the GPU. So then you ask the OS to do the swap for you, and you say, okay, now save the register file somewhere in the memory, save the register file from the other thread, and run the other thread. So you see all this. This is called context switching. But on the GPU, you don't have and this is very expensive. On the GPU, the register file is partitioned. So all the threads have their own registers, their own state on the GPU. And they cannot get out of the GPU, they cannot be swapped out, unless they finish. So this allows the warp scheduler to be very efficient from moving from one block to the next, the execution. And this allows you, or from warps to warps, and this allows it to hide efficiently the memory latency. That's a key architectural change of the GPUs and the CPUs, and why they can accommodate so many threads and execute them efficiently. The other implication is that these are not yet scheduled for run, these blocks, you see? So, and as I said, they have to go to finish their execution before those final 8 blocks will be scheduled for execution. Okay. We will see in a bit what are the implications of this model. Next thing is, I said before that all the 32 threads of a warp execute the same instruction. But actually, you are allowed to do branching. So you can have in your code something like that. I don't know if you can see it. If my thread ID is less than 4, then do A and B, else do C. That's pretty much valid. But how this translates, because from the hardware there is this limitation that they have to execute the same instruction, but how this can be possible when I have a branch? And so this is possible with what's as follows. So when the warp gets into a branch, what it does, it checks that it checks the condition basically and says, okay, now I'm executing this branch with the first 4 threads, and I deactivate the rest. I'm executing A, I'm executing B, then I deactivate the other part and execute the else part. So effectively, what has happened here? So, well, I mean, not else here, but it's if it's the other condition. So effectively is that, yes, both branches will be executed, right? So you see that instead of just the 4 threads executing 2 branches, 2 instructions, they all execute 3 instructions. And instead of this branch to execute just 1 instruction, they execute basically the whole if block. They pseudo execute because they are deactivated. But in terms of cycles, it is. Let me just bring you the microphone. No, it's just for recording reasons.
It's really just
this
is really just a small question. Am I wrong if I say that this now is sequentialized? I mean, it's run sequentially instead of...
No, the individual, the A and the B, they are again parallel. I mean, the A and B executed by 4 warps, by 4 threads, and the C by 28. But both the branches are serialized. So yes, they are both branches basically are executed, and half of the threads are doing no ops. So this phenomenon, this situation is called warp divergence. And with the newer architecture, the latest architecture, this is relaxed with the Volta architecture, but we're not going to cover it. I don't know if Marcus, you can just introduce tomorrow a couple of slides of what Volta architecture brings. I don't know. So this is what we said here. So what are the implications of this memory model? Well, one was what we've said about the divergent warps. We have redundant execution. But there is a more important implication from what I've shown before with the blocks. And first of all, okay, this is what we've already said before. We need to have lots of active warps, lots of active threads, lots of active blocks in order to hide the memory latency. We need to have lots of pending stuff so that when a thread blocks or a warp blocks in a memory access, then there should be enough to be scheduled after it. But what is important is this thing. There is no way to do global synchronization within a kernel. Like a global barrier, like an MPI barrier, or like an OMP barrier that is across the whole threads. That's a different thing. You cannot do it. And why is that? Because I'm going a bit back to this slide. A block will run to completion before it's moved out. A block cannot be preempted, like on the CPU. So this block will end. So if this guy waits for this guy, then this cannot happen. So that's why you cannot have a global synchronization within a kernel. Now, but on the other hand, you can synchronize across kernels, and that's a typical way to work around this. But that's a typical difference between the CPU and the GPUs, and the way we have been programming until now with OpenMP and MPI, assuming, okay, I'm doing the global synchronization. No, on GPU, you have to launch a different kernel. So let's move a bit now to the memory. So the architecture is, there are several memory levels. One is, the first of all is you have the global, what's called global memory. It's like the main memory of the GPU, and it's usually on the Pascal GPUs is this high bandwidth memory technology, like on the KNLs, and it can see fairly high memory bandwidth values. Now, it's accessible from all the threads of all the gangs, that is, from all the blocks. It's globally visible, that's why it's called global as well. Another important feature is that the data is persistent across kernel invocation, and that allows us basically to copy data before, have the data there, call kernels to work on the data, and then move out the data when we're done with that. Another important feature is that the memory accesses done by the threads of a warp may be coalesced. Coalesced means that they are grouped together in a single transaction if they meet certain requirements, and that's also crucial. And it's not so, in the CPU you don't have that notion so much. In the CPU, what happens? So assume you have an array and you bring AI, the ith element, then what's going to be brought? It's going to be brought a full cache line, and this cache line will be put in the cache, although your next iteration does not access the i+1, but access something else. Here you don't have this notion of cache in the sense that I get a cache line and have it there. But on the other hand, you can the memory access from successive threads in a warp may be coalesced in a single memory transaction. So if thread I accesses the ith element, thread I+1 accesses the I+1 element, and so on, all these 32 elements will come at once to all the warps. This is called memory coalescence. It's quite crucial for performance. But again, the common notion here between CPU and GPUs is that you need spatial locality. Now, but in the GPU, it's not just spatial locality on the axes, but it's spatial locality on the axes across the threads. It has also this dimension of the threads. So next is it everything here? Any questions? Next is the shared memory, or L1 cache. It can be used as both. You can either configure it to be acting as just a standard level 1 cache, or you can manage it yourself. And this is shared among the threads of a single thread gang, or a CUDA block. So because as you remember, this is part of the SM, and since a block can only run on a single SM, then it cannot view the shared memory of other SEMs. Now, it is quite fast, so ideally it has a one cycle access if there are no what's called so-called band conflicts. So the threads of a warp should access different locations of the shared memory. If they don't do that, then the latency, if all of them they just go and grab a single element, then you will have a latency of 32 cycles. As I said, software or hardware managed, and there's no coherency across SMs. So like with the caches on the CPUs, where you have a cache coherence protocol. So if something is invalidated on one cache of a core, then through that protocol, this change is communicated to the other caches. There is no such way. And there's also no sequential consistency, so you have to synchronize your threads with special directives to make sure that some memory operations have occurred to that memory. But these are details. I'm just going through them just to give you an idea of the architecture, because in profiling you might see all those stuff. In OpenACC those are hidden, but that's the idea. Now, another is the local memory. This is not visible to the programmer directly, but it's visible to the compiler. And this is usually where the compiler, the memory that the compiler uses for putting automatic variables. And the important thing here is that this part of the global memory that is cached, I think. And the thing is that usually for those that, if you see that you have very large register usage, then the compiler may decide that, okay, in order to increase a bit of parallelism and occupancy, I will spill some registers. Register spilling means that ideally, I would have to have my variable on the register, on a register file, but the register usage is so high that I use a memory for that. Usually on the CPU, the compiler uses a stack, but here it uses this part because GPUs do not have a stack. So, and this can be a performance problem. The other thing is what's called constant memory, which is for storing constant values, and this basically is cached. Usually, for extreme optimization, you may place stuff there. And then there is another that's called texture and surface memory. This comes from the graphics background of the GPU, because remember that GPUs, their major purpose some year ago was to render graphics. So this is optimized for two-dimensional axes, which is not very, so you can access something towards the direction and towards the other direction efficiently. And they are also processed in special units, but I'm just mentioning all those here. So how do we program the GPUs? Of course, there's CUDA, which is the low-level interface. And you have, in order to go that way, you have to have an understanding of the architecture that I've showed you before. And all these details that we went quickly through them, they're much more, believe me. And if you want to get efficient code, you have to be able to know correctly the architecture. It's low level, more code as a result. And as I said, good understanding of the GPU architecture to get efficient code. But on the other hand, you can, since you have control of the shared memory of these different texture memories, you can do your own warp scheduling somehow. You can do lots of optimizations. It can give you higher performance at the cost, of course, of more effort. And the purpose of this course, though, is that we're going to see the easy way, and which is also efficient, I would say, of doing it, which is using directives like OpenACC or the OpenMP 4.5. In this course, we're going to cover the OpenACC. It's easy to use and productive. And the other thing is that you don't have to do very intrusive changes in your code, like with OpenMP directives that you would otherwise have to work with your own thread pools, etc., p threads, etc. Here is just again some directives in your code, and we'll make it run on the GPU at the very good performance level. It's only I would say from my experience is that only for cases that you want to do very specific optimizations, like getting access for the shared memory and boosting the performance to the maximum, then the way to go is CUDA. But if you just want to quickly enable your code for the GPU and have a decent performance, directives is the way to go. More on it after lunch. So here I finish this introductory part, and I'm happy to get any questions. Okay, how did it feel? Did you have already an idea of the GPU architecture before who was the first, who had the first encounter with GPU internals somehow? Okay. Okay, that's good. Yes, please, just a sec.
So there are blocks of GPUs, so there are blocks of threads.
Mm-hmm.
So, and to use them, is it only, we can only activate one block fully? So we cannot use 1.5 blocks, for example?
No, you cannot. It's basically you don't have control on how many are the active blocks. This is determined somehow implicitly of how many of them can be accommodated on the GPU. And yes, you cannot activate a half block. The whole block will run.
And who control how many blocks will be activated?
This is determined implicitly. So assume that I will give you an example. So you have like a 4K array with 4,096 elements, for example, and you have a block that is 1,024 threads. Then automatically you will have 4 blocks. So this is how it's determined. If you were writing CUDA, then you would have to do this division yourself. So this is my iteration space. Then my thread has 32 or 64 threads. Okay, I need so much blocks. OpenACC does this for you automatically.
Okay, yeah, thank you.
To add a comment to that, basically the mapping into blocks and threads is something that if you were writing CUDA, you would have to do that kind of arithmetic in your code. You would have to, at some level, deal with that. The directive-based methods like OpenACC and OpenMP, this is all done under the hood by the compiler. The compiler sees the iteration space of your loop, it figures out some way how to partition that into blocks and threads and so on. So it's more important as a concept for how your code gets executed on the GPU, and you will see when you look at profiling data that those numbers show up, and it is good to know about it because sometimes you need to tune it a little. But it is not something that you have to program yourself or have full control over it. And one other comment as an addition to CUDA and OpenACC, it's also something where the landscape is changing in terms of what the compilers can do. Until a couple of years ago, it was pretty much a rule of thumb. If we looked at a whole range of different applications that were written in either CUDA or were using OpenACC, that you would typically achieve something like 60 to 70% of the performance of a well-tuned CUDA code when you were using directives. So it was basically a trade-off of 20 to 30% of the performance for a much easier programming model. But that is changing. We have codes now that have been written by pretty well-trained CUDA programmers, and the OpenACC version of the code that somebody developed in a couple of months later reaches the same performance. So those things are really changing, and sort of you can still write the fastest code in CUDA, but the amount of work required to do that is much higher. And it is also something, if the architecture changes or your sort of the knobs that you tune to make it work efficiently on a given architecture, if those things change, you as the programmer have to go in again and spend some time again to tune that. Whereas with the directive-based model, for example, OpenACC, that's all done by the compiler. The compiler will know, oh, now I'm generating code for another architecture. Here, the ratio between the memory bandwidths of this instance and that instance is another factor than on some other architecture, and it will tune accordingly. So it's much less work to put in like that. And It's certainly not true anymore that generally you give up 20 to 30% of the performance relative to a very well-written CUDA code. It really depends on the applications. We see some where the OpenACC code is about as fast. We see some where it is actually faster on production level code than CUDA code that was written about a year or two ago, because you would have to go in and really tune it again. And sort of that margin is kind of shrinking, and it's blurring a bit more. There are things that you can tune very well in CUDA, and there's certainly some kernels where that can be a very useful thing, but you all also come from very different applications, right? If you're working on weather models like you, for example, those things are easily several 100,000 lines of code. If you want to rewrite that in CUDA, and then 2 years later you need to go in and tune it again, or change some algorithm, and you replace those 300,000 lines with another 350,000 lines and so on, that's a lot of effort. Whereas a directive-based approach makes it much easier to migrate across architectures, to change an algorithm at some time, and to work on individual parts of the code without having to change all the rest of it as well.
Okay, so now if you don't have more questions, I will go to the next part, which is introduction to the programming environment here that we're going to work. I'm going to give you also your usernames and passwords. Let me just... Okay, so this is it.
What is GitHub repository?
Excuse me?
GitHub repository for the presentations.
Yes, I can show you again. So the GitHub repository is vCarak OpenACC training. And inside the slides. Okay, so before starting with that, I will need to give you the passwords and accounts. Okay, I would... Okay, you can, I would say, you can get one here. It's an account and a password.
Just take anyone randomly, right?
Just pick one. Okay, so have you all taken? Okay. So first I'm going to give you an overview of the system, and then how you access it, how you compile the code. Okay, this is a bit general because we're giving you the make files. How do you run the code, generally, editing, how you transfer files, and then I'm going to have a couple of slides explaining a bit the repository of the course and its contents. So meanwhile, I would suggest, while I'm showing this, also to try the different steps. So in case you have a problem, just tell me, and we can contact the system administrators to fix it. So, Pete-Stained is a large supercomputer. It has basically it's a hybrid XC40, XC50 crazy supercomputing. So it has basically two major partitions, I would say. One is the large one, which is the hybrid nodes, which is 5,320 nodes. And it has each node, you remember in my introductory slides, I showed you it has one CPU, one Haswell CPU of 12 cores, and one NVIDIA Pascal GPU. And then we have the multi-core nodes, which is 1,813 nodes. And it has two Broadwell processors, so it's for multi-core jobs. Then we have 5 login nodes, where we have very large amount of memory, because this is where we usually compile and do all the preparatory stuff. We don't compile on the compute nodes. Basically, actually, we're cross-compiling. I will show you how. And the interconnect is the Cray Aries, and with the Dragonfly topology. Now, regarding the file systems, just again information a little bit. There is the Scratch file system, which is a high-performance Lustre file system, which is also the recommended file system if you want to do heavy I/O. We don't have to do heavy I/O here, so we will still keep working in your homes. But it's important to know if you have allocations here. It's accessible in every system through the $scratch variable. Then we have the users, which is the GPFS file system for users' home, and then project and store, which are for computational projects. And you can find always generally, if you're a user of Pete-Stained, then this is your user portal. We have all the information. Some of you may have already gone through it. Now, so accessing Pete-Stained, Pete-Stained is not visible directly outside CSCS. So you have to do two hops. One is you have to go to the front-end nodes, which is this Ella, and then from there go to Dained, which are the nodes are called like 10 and the number, which are the login nodes, and they are the compute nodes. So I would ask you now to log in with your accounts. You may also forward the X. Actually, we might need it for debugging to show you if you want to try. And we will certainly need it in tomorrow's hands-on session. So I would say try first to log in and tell me if you have problems with your passwords, and also try to log in on Dain. Yes, please. You have a problem?
I don't have a computer with Linux installed on it.
You can use PuTTY. Do you know the PuTTY from?
No, I cannot use PuTTY on my PC, on my computer.
But you don't have any SSH client or something? So yes, and then you can work with one of your colleagues or something like that, because.
Do you have some PC I can use?
I should ask for that. Let me ask at the lunch break. Okay. Yes, please.
Can I just start with Wi-Fi access, because I've never studied anywhere around Edinburgh.
The Wi-Fi. Yes. So try for the Wi-Fi. Yeah. No, the Wi-Fi should be. Okay. If you connect to I forgot that. See, it is CSCS, then it should be plus CPU plus GPU. I should double check.
With the plus sign or?
The plus sign. I should. The Wi-Fi is plus CPU. So if you connect...
It used to be like that.
Huh?
It used to be like that.
Yes, I don't think it has
I
changed.
didn't check now, but it used to be...
Okay, it was plus CPU, yeah. So just tell me if you were able to connect. It works?
When I do SSH, it just takes forever. Is it normal? Oh, now it works.
Ah.
Okay. Yeah. I think I need it to... Yeah, okay, thanks.
Okay. So are you all on Daint? You should be seeing something Daint 101, 102, or something like that. Okay, so while you're trying to connect, moving forward, so the operating system is Linux, but a special Cray flavor. They're called Cray Linux programming environment. That it has its own intricacies. It's not usually, if you're not used to Cray before, then it's something new. It's not like normal Linux. Well, I mean, it feels like, but it has some stuff they're not so. When I came here, I was not used to it in any case. So basically, it gives you 4 compilers. So you have the Cray compiler, which is the default, the GNU, Intel, and PGI. And accordingly, you have 4 predefined programming environments, which are available as module. We're going to see the notion of module in a while. That's PRGN, Cray, GNU, Intel, and PGI. And if you are now on the Daint, on the login nodes, if you do this thing, echo PEN, you should see either Cray, GNU, Intel, PGI. So by default, you should see Cray. It's a way to differentiate. The important thing is with these environments is that they provide you with wrappers for the compilers. So you don't have to type GCC or Cray CC or something like that. Instead, you use those wrappers. FTN for Fortran, CC lowercase for C, CC uppercase for C++. And those wrappers are taking care of setting out the correct optimization flags for the target architecture, also for linking with the correct libraries and so on and so forth. And they are also required for MPI programs because we have the MPI is the Cray implementation of MPI-CH, and this is there's no such thing as MPI-CC, MPI-CXX, or this kind of stuff. It's just CC capital or CC lowercase. So, for managing the software, perhaps you have seen also in other supercomputers, and those that you have been here, we have projects here, you know it already, uses what's called environment modules, the TCL implementation called TMOD. So the idea is that you don't have to, every time you load a module, to set your path and all the variables, and this program does it for you. So it modifies dynamically your environment with what's called module files. And all programming environments, those PRGN, GNU, PRGN, Intel, are all modules. And now the compilers wrappers that I showed before will detect this environment and set up accordingly for each of it. So here is example. So for example, to list what are the currently loaded modules, when you enter the system, there is a set of modules loaded. So here you see PRGN Cray, you see the MPI. Also, you see this thing which means that your target, now if you try to compile now, your optimization, your flags, etc., will be for the Haswell, so the Haswell node, and not for the GPU. That's especially true for the Cray compiler, so if you try to compile with Cray compiler an OpenACC program, and you have this thing loaded, then it will just ignore the OpenACC directives. Now, when you want to switch to a different programming environment, you use the module switch command. So for example, here I switch to PRG and PGI to get the PGI compiler. And then they do a module list, and you notice that the difference in the module here, I have PGI, I have also the PGI compiler here, and also there is a slight difference that there's no version of the libsci library, because Cray does not provide. libsci library is a LAPACK library, high optimized library by Cray, and does not provide that for the PGI. So you see the module switch does all this stuff. And also now here the FTN points to the Fortran 90 compiler, to the PGI compiler, whereas, okay, before I haven't run that. So now I switch back, and then you see that the FTN now points to the Cray compiler. Okay, so for loading modules or unloading, there's those two commands. And for example, here I'm loading the Cray SDF5, and then makes available this command, which is located here. If I load it, there's no such thing. And if I try to run, there's no such thing. So it dynamically updates your environment. Now, for software, we will need that for the DDT. I mean, when I will show you the debugging. All the software stack that we see at CSCS make available to our users is available through a parent module called Dane GPU. So you have to load this, and then you get a whole list of software that's built for the system, where you can select what to load. Another useful command is the avail command, which shows you what are the available, for example, takes the name of a module and then the available versions. Another command is the show. So the show basically shows you what this module sets as variables, so you can know the path, you can know if you want to debug something, or if you check exactly to what library you're linking, and so on and so forth. And the help, which is just a help message for the package. So let's move to a bit more interesting stuff. And here I will ask you, have you all be able to connect and play a bit with those commands? So for submit, all this was done on the login nodes, where we also do the compilations. Now, to run on the compute nodes, you need, when you go through the job scheduler, and on Pitstein we have native Slurm, which basically means that you submit Slurm to the compute nodes, and in order to run an MPI process, you use the srun, no such thing as MPI run or something like that. So there are two ways of submitting jobs. One is interactively from the login nodes using directly the srun command. It's like using MPI run directly from the login node, and this will create a job allocation implicitly and then go to the compute nodes and run there the srun. And also with the sbatch command, which takes a script that you submit as usually in those systems. So necessary and useful options that we're going to use. First, running with the srun command, but those are valid also for the sbatch. First of all, this is required. You have to specify the subset of nodes of the system that you want to run. There are basically two major partitions, so to say, virtually. One is for the hybrid nodes, which you take by putting this option. Otherwise, you will get an error message immediately that you have not specified one. And the other is MC, but we don't care. So minus C or minus constraint equals GPU. Then for this course, we have a special reservation that's called OpenACC so that we can get quickly allocations. And I suggest always passing this flag if you want. We have, I think we have 20 nodes, no, 16 nodes allocation, which is enough. Now, another option is minus n capital is the number of compute nodes to use. And minus n lowercase is the number of tasks. So if you just put this one, minus n2 without this, then you will have 2 tasks per node. And another useful, especially when you're running on the system small jobs, is the duration of the job. So you basically tell to the scheduler, look, my job's gonna get more or less that time. So the idea is if this is accurate enough, then if you have very small allocations, so okay, I just want to run something for a minute, the granularity there is a minute, then the scheduler may just backfill you in the queue so you can quickly run. Otherwise, job will be killed at the time limit, and the maximum time slot is 24 hours. So let's see how one can run. I suggest you try this as well, but I would suggest pass also the minus reservation equals OpenACC. So I haven't done that yesterday when we prepared this, because the reservation is valid from today at 7, so it's from 7 a.m. to 7 p.m. Today and tomorrow. So here I'm just running host name on 2 nodes, and then you see I've landed on 2 nodes. Then you see that, as I said, the computer nodes are named like NID, etc. And if you just say minus n lowercase 2, you get on the same node. Okay, I suggest trying this as well. Yes.
Do log SRAM or something, because when I do module list, I don't have any modules installed.
Because you are on Ella, you have to go to Daint. Now here,
I see. Yeah.
This is the front end nodes.
Okay.
So you have to use SSH, Daint, and that's it. And I will ask you again.
Yeah. Okay.
For the password. Make sure to be on Daint, not on Ella.
Reservation is OpenACC or?
It's OpenACC, a single board.
Oh, like this.
Yes.
But then it says that the project course is either specified at submission, unable to allocate resources.
Oh, wait a second. I will investigate it, but try to use the minus A capital option. Courses.
Here? I just put here minus A.
Yes. Minus A capital, yes, uppercase, and then courses. Yes. Try this one. What have they done? Let me just try myself as well.
But I did like module load GPU. Does it affect something?
No, it shouldn't. It's something unrelated to that. Okay, I'll try with a course account. No, first of all, I'll try with my account. Okay, for me it is. For me it works, but now let me check with. For 0, it works.
The order of, I think, host name and reserve ACC matters maybe.
Yeah, the command should be always at the end. So here are the options for srun, and here is your command and its argument. So were you able to run on the reservation? What are you getting? Did you?
Yeah.
Okay. It doesn't?
I have exactly same command as yours now.
Okay, so just tell me the usernames. I will write them down. So who wasn't able to run? Okay.
Was unable or able?
Unable. Okay. So can I mean, what are the, so 86. Okay, just tell me the number. 80?
87.
87.
85. So the two high ones.
96.
Okay. 91. 83. Okay, they have set up something wrongly. And? 98. 98, 97. Okay, but for who has it worked? Okay, and yours are?
92.
92.
82.
Very strange. I will ask during lunchtime and to check those accounts. That's really, really strange. Anyway, nonetheless, I think if you meet the reservation, you should be still able to run, or?
So do we need the super user, the SNU?
Excuse me?
No.
Okay, can you type this thing, those that you have failed?
Same as yours. Yes,
Same. Really strange. And all of you have tried this thing. Okay, I will ask the guys. Anyway, let me just move a bit forward. Then we'll have some time before the hands-on session again with this. Okay, so.
Also a remark, the slides are not getting compiled.
Then?
There is some image missing on the slides, so it gives an error.
Wait, no. This is just the sources. I would say I have put the PDFs.
Okay.
I have put the PDFs on OpenACC training, not OpenACC training slides.
Okay.
But thanks for that, because I should put the figure in any case. Yeah, the slides, you don't need to get the raw sources from the slides, because I have a repository that's OpenACC training and another one that's called OpenACC training slides, which are the sources of the slides. So you don't need that, you just need the OpenACC training, where we have also the exercises and the PDFs of the slides. So, so here is how we, with the other way to go with SBATs. And here you have a job script. And the key here is you have those directives, starting with SBATs. The key here is, because lots of users sometimes are confusing and we're getting tickets on that, is that here there should be no space. Has but no space. Otherwise, it's just a comment. Here you have also some special variables that are set when your job is submitted. And you just submit it like that, s-but job.sh, and then you have this command that you can either use with -j and check a specific job, its status. So here is the account, my user account, the name, which is this thing. The status here is completing, and some other information. Or you can use -u, your username, to get all your jobs. And if you don't want to remember, which was my last job ID. And then you can see your files. If you don't specify something for standard error, then it will go to standard out. And so here is the output. My job ID was that, and the host name was that. And then you get also some information about when your job was submitted, when it was eligible to run, when it started, ended, and so on, and some energy information. So that's informational. Okay, I will just take 5 minutes from the break. Other useful smart. Okay, I saw you the SQ already. Another is scancel, your job ID to cancel the job. Then it's also scontrol. You won't need that, just to get some more detailed information about the partition reservation, etc. So, for example, here is our reservation, and you see that the account should be. Yesterday it was inactive, but today it must be active. So it's from 7 to 7. These are our nodes, etc. Here, there's the partition. This is the whole system. You see 7,000 nodes. Okay, editing files. There is VI, Emacs, gedit if you have X. And you can copy files with SCP or rsync. If you use rsync, just make sure to put the slashes correctly, because it means different things. Okay, so that's for now. And I don't have anything else. Okay, so I suggest then going for lunch, and we continue after it.